Alrighty. Thanks everybody for being here. It's kind of a big room. I know we're a little bit far away, but this is the best we could do for a screen. So we're going to stand near the screen and hopefully, can you hear us okay? Yep. All right, I guess this is a theater, so it's meant for this kind of thing.
Yeah, maybe.
Awesome. Well, thanks for being here, guys. Thanks for joining us for our strategic design talk. We're going to do brief introductions really quick. My name is Mike Corsetto. I am the head coach for Team 1678, the Citrus Circuits. In my day job, when I'm not doing fun robots, I'm doing work robots that also happen to be kind of fun. I'm the director of hardware and systems engineering at an ag tech startup company called Advanced Farm. We build robots that pick strawberries and apples. You can check out our website at advanced.farm if you're interested in learning a little bit more about what I do. But it's a lot of fun. I get to work with a lot of really smart people working on hard problems in ag tech. And from FRC perspective, I'm going into my 20th year in FIRST. I was a student on Team 114. Any Eagle Strike folks in the crowd? Yeah, let's go, Eagle Strike. And then I started mentoring Team 1678 when I went off to study mechanical engineering at UC Davis. And a lot of the credit that we can give in this presentation is to a lot of other really smart people in the FRC community. We learn a lot from, especially from our neighbors 254, Karthik, a lot of other influential mentors and teams in the program. So a lot of the stuff you're going to hear today is regurgitated information from those teams. And some of it's a little unique to Citrus, but a lot of it is knowledge that we've gleaned from other teams in the program.
Hi, I'm Austin Haddox. I am a strategy, scouting, and mechanical mentor on 1678. As my day job, I do data modeling and reporting for businesses. So if there's any questions that they have, I dive into their data sets and try to evaluate, why things are happening. And so I try to, bring that to FRC too. I'm going into my 11th year in FRC. I was originally a student on 2085, which has kind of formed into Hydra Robotics. Do we have anyone from Hydra? No? Okay. And I started mentoring 1678 in 2019.
All right. So a little overview of what we're going to talk about today. We're going to go into some things you can do in the preseason to improve your team's chance of success going into the next kickoff. We'll talk a little bit about drivetrain, mechanism design. We'll talk just very high level, some strategies on electronics, on programming that can help equip your team for success going into the season. And then we're going to get into the meat of it and talk about how to strategically manage your build season to properly utilize the very limited resource of time that every team is given to maximize your chance of success. And then we'll talk about the competition season, what it looks like, how you can improve your team's chances of success. If you have questions are great. We are going to try to get through the material as quickly as we can to have time for questions. But let's save them all to the end. So write them down if you have questions, and then we will have time at the end for questions. And if we don't get to your question during the Q&A time, we will be around after the presentation, and you can ask us questions then.
So the first and foremost rule of strategic design is to keep it simple. No overcomplicating designs. Build within your team's limits. Know what your team can build. Build within what you know. And once you design something, don't overcomplicate it. Redesign it. When something breaks, make it simple. Make it so that you can, so that it doesn't break continually. And function over form, right? There's a reason why our robots aren't powder coated and painted every year, and that's something that we want to keep our beauty on the field.
It's a good
Not in pictures. It's
a good way to put it. Okay, let's talk a little bit about, now that we have that covered and with that golden rule in mind, let's talk about what you can do in the preseason. On 1678, the purpose of preseason is for training. Training is probably priority number one for our program during the preseason, aka from now until kickoff. We really think it's important that our students are well equipped before going into kickoff so that we spend as little time during the season learning new things, and we spend a majority of our time during the season building new things based off of the skills and experience that our students have built up until kickoff. So trainings are really critical for 1678's fall portfolio of things. For our more veteran students, we use the fall as an opportunity to try out new things. Maybe it's building a mechanism that some of the team members have never built before. Maybe there's parts to our code base that our software team is hoping to improve. Our scouting software subteam right now is working on squashing a whole bunch of bugs and things like that before we go into the next season. So everyone's trying out new things. So it's not just bringing your new students up to speed with all the tools and experience they're going to need to have going into the season, but it's also about trying out new things and expanding your team's capabilities like Austin talked about in the last slide. And then we'll get a little bit more into this right now. A great time to learn about FRC past is during the off season. Especially our strategy team that Austin's a part of spends a bunch of time in the fall studying old games, quizzing themselves on old games, talking about the various strategies that developed, but also just about like the build philosophies. That's really important to know what was done in the past, because a lot of times the games can have some aspects to them, and we'll go over that in a little bit. Okay.
So great off-season projects that are always go-tos. Designing new shooters, intakes, elevators, climbers. If you have a spare kit bot that, or kit of parts drive base that you guys have laying around, it's a great resource to have students know how to put together a drive base really quickly. And it's great that it comes with instructions. And just any drive base in general, we're going to get to this later, but drivetrain specifically, build within your means is kind of the whole purpose of this presentation. And so, especially with all the new drivetrain options, it's really important to test out and try to design those options during the preseason before you go and try to implement those during the season.
Totally. All right, we talked about game history. Learning game history I think it's really fun to be able to go back to Blue Alliance and watch old match videos and see how old games were played. But it has more of utility than just being a little bit of an entertaining side exercise. There's actually a whole lot of things that you can learn about how to build good, simple robots to manipulate various game pieces or accomplish certain game tasks. A great example is from hanging inner tubes in 2007 and then again in 2011. The robot on the left is a robot from the 2007 game, and then the robot on the right is a robot from the 2011 game. And you can see how both games actually involved inflatable inner tubes of almost the same diameter that were being scored on hooks. One hook that was roughly 2 feet off the ground, one hook that was roughly 5 feet, and then one hook that was roughly 8 feet off the ground. Now, there were different end games and all sorts of other different elements that made the games different, and the scoring calculations was different, where the game pieces actually went on the field was different. But the core competency of picking up a tube and placing it on a hook, one of which is low, one of which is medium, one of which is high, was actually fully correlated between 2007 and 2011. So just as a brief aside, 1678 in 2011, as a part of building our claw that year for the game piece, we took a picture of Team 100's claw from 2007, and we put it up on a projector. This is before we had any machine tools or anything, and we traced out the shape of the claw on a piece of sheet metal, including where the bearings went and where the wheels went. And then we put that to the bandsaw and cut out the claw, and then we drilled the holes for the bearings, and that was our game manipulator for the 2011 season, based off a picture that Team 100 posted in 2007. So those are kind of the elements that can really shortcut your design steps and get you to a workable solution faster. We wouldn't have been able to do that if we didn't know about the similarities between 2011 and 2007. And there's a bunch of other examples here of different game pieces that we saw similar styles of play between seasons.
Yeah, so this leads perfectly into golden rule number 2. Steal from the best, invent the rest. We're not going to pretend like we're the best designers in the world. There's plenty of other teams that can design much better than us, and they already have. So why would we reinvent the wheel? There's going to be other examples later in this presentation about specific examples that have just been recurring designs that the reason why they're staples in first is because they work. And, like Mike said, 100 in 2007, if we didn't know about that, we would have been forced to come up with our own manipulator to try to intake and score those tubes. However, if you know those, if you know your FRC history and you know what designs were successful, it's pretty easy and effective to implement, the top designs from previous years, because normally they're a lot more simple than you think. And a great resource is Robot in 3 Days. I know that they don't post as much as they used to, but it's still a great resource to see how other people are tackling that year's game, and those specifically the game pieces, and seeing how it moves through different designs.
All right, let's talk a little bit about drivetrain. All right, so we have a little bit of an exercise here. We have a bunch of pictures of robots, and I want a brave audience member to tell me what's the same about all of these robots. Anyone have any ideas? What's the same about these robots?
See a hand in the back.
Yeah. They're West Coast Drive. Look at this. Normally I get an answer of they're all blue. That's usually the first answer, which is true, but not the point of the exercise. They're all utilizing very similar concepts for drivetrain, aka wheels on the right and the left side that are independently powered to propel the robot forwards and backwards and to make turns. All of these robots were regional winning robots. All of these robots were world championship contender robots. And the only reason I bring this picture up is because this team did a great job utilizing this design to a lot of competitive success. And I like to say that, if it was good enough for them, it can be good enough for your team, right? And that's not to say it's the only choice, but the golden rule is use a proven drivetrain for you. That's the really important part here, is the shortcoming that I see teams get into is they try a new drivetrain style during the build season. And that is absolutely not the way to approach a season. It can totally derail your season, because beyond anything else, the most important thing you can do any given year is drive, okay? And teams that show up with either non-functional or poorly functioning drivetrains stand little to no chance of being in a picking position at the event or being picked at the event. Driving is baseline number one requirement. Not just driving, but good driving. And so as one example, for years and years and years, 1678 built tank-style drivetrains, West Coast-style, whatever you want to call it. And for the first time in an official event in 2022, we competed with a swerve drivetrain. Now, I know a lot more teams are using swerve drivetrains. It's really cool. It's a really cool concept for moving the robot around. But the swerve drivetrain we competed with in 2022 was the 9th swerve drivetrain robot that we built on 1678. It took us 8 iterations of building swerve drivetrain robots to get to the point where we felt comfortable enough with the build style, the module we were using, the controls, the autonomous mode, the teleop driving. There were all sorts of nuances and bugs that it's things that may seem frivolous, but like, for example, all of off-season in 2021 until I think Madtown, we would end autonomous mode and not know which direction the robot thought it was facing. Yep. And they'd always have to reset the gyro after every autonomous mode before they could start playing teleop. And you can imagine that process would take 5-10 seconds every single match. Every single match we played, autonomous is over, turn the robot around, press the reset button. Okay, now you can start playing. And it took the team, like those are very small things, but they impact if you can drive or not in the match. And again, driving is the baseline, most primal expectation of what you do as a team. So my advice is either build stuff in the off season and get it dialed, but if you don't have a different drivetrain done perfectly, you got to stick with something simple like a tank style drive. And I absolutely love the Kitbot for a whole lot of reasons. I could talk for days about why the Kitbot is awesome, but the primary reason is it's a known entity. It's known how to control it, and it lets you spend a lot more time on other mechanisms because you basically build it in a day and you're done, and you can move on to the things that are actually going to score you points in the match. So just a brief pitch for the Kitbot, but more importantly, the golden rule here is use a drivetrain that your team in particular has personal experience with before the build season. If you go into next build season, you should not, I will say this very confidently, you should not under any circumstance be proposing a drivetrain style that you have not built and conquered in the offseason. I'll leave it at that.
Well, I would say the biggest thing is you don't know what you don't know.
Yeah.
And coming into, especially when it affects driving and that you can't do anything else in the match without that.
Agreed.
You can't.
Agreed. I will skip this story for right now, and we will go to mechanism design. Austin.
Okay, cool. So with mechanism geometry, there's a few key aspects and tricks, right? You want to have minimum degrees of freedom, so you want the least amount of moving parts on your robot. If you look at a robot this year, there's a reason why we didn't have a turret. It's another thing that we would have had to, another thing that can break, another thing that we would have had to control for, another thing that we would have had to program. It would have changed vision. It's a lot of different things as you want to minimize the amount of moving parts on your robot. Now, with low center of gravity, how many of you guys have seen a video or seen in person a robot tip over in a match? Yeah, I should see everyone's hands up. If your robot's on its side, it can't score any points. It can't play. And so when you have low CG, it makes everything just more reliable. It makes you sink into the ground better. It makes it so that you're less tippy. You're more reliable when you're driving. It makes climbing more reliable. You're not going to be swinging as much. It just makes things a lot easier to manage when these corner cases happen within matches. When it comes to symmetry, it's really hard to build an effective asymmetric bot. Especially it's hard to drive an asymmetric bot because when you're on the field, it's hard to orient your robot when you have to orient one side versus another, when it's just compared to the front versus the back. And then when it comes to staying inside the frame perimeter, when you look at a lot of the top teams, you look at 971's intake, right, comes in and out. You don't want to have, especially now where they have penalties, where if you run your intake into other robots, you're going to get a penalty. You want to be able to control your intake and your shooter and all of these other things that stick outside of your robot, because if you run into another robot, you're going to get fouls, you're going to break them, and you're not going to be able to play effectively in the match. And when you're outside the frame perimeter, like I said, you want to be robust. You don't want to be breaking in the match because that's the thing that's going to be derailing your matches and your seasons the most.
All right. A couple other key points. I'll talk about the difference between motors and pneumatics, or at least how you should think about them in your design. As far as motors go, they're really great for motion, especially motion on your drive chassis. They allow variable movement, fast spinning wheels, things like that. The tricky part with motors is if you're using them for any sort of precision motion in a mechanism, it takes a little bit more software chops to get that to work properly. You can think of having a in and out intake versus having an intake controlled by a motor where you can set it to any angle you want to. The latter sounds a little cooler, but in practice, it can be harder to tune that system. Not impossible, but just a little bit more work. So that's where pneumatics come in. Pneumatics are really great from the perspective of they're super repeatable. They get you from point A to point B. A good example from our 2013 robot, you see it's hanging on that bar right now. It only had to lift itself up a couple inches, and so the little pneumatic hooks would just go up a few inches, we would drive into the bar, and then they'd pull down a few inches, and we were hanging. And it's consistent. You knew how high it was going to lift up. You knew how much force the pneumatics had, and it was a pretty simple system to put together. The challenge with pneumatics is you're using an air compressor and an air system, and we won't get into all the math and science behind it, but the air compressor that they use in FRC, if you measure the wattage you're getting out of your pneumatic system versus the wattage you put in from the battery electrical power, it's not a very efficient system. You're getting a small percentage of the overall power output of the battery versus an electric motor is putting out a little bit more wattage per wattage in, higher efficiency. So not something that's really, we don't need to go into it right now, but it is something that weighs into how we choose to design some mechanisms. One quick example is if there's something you expect to use tens, if not hundreds of times in a match, you may want to consider the difference, the trade-off of motors to pneumatics more often, because if there's something you're trying to actuate a bunch of times in a match, the compressor can only do so much. It can really only effectively fill I think 5 large Anti-Mark tanks in a whole 2-minute match. That's if it's running nonstop, which is generally not good for it. So you got to consider, am I going to be using this mechanism a lot? If so, pneumatics are probably out of the question. Or does it require a ton of power, like a very large, you see teams sometimes trying to hang with very large stroke pneumatic cylinders that take a bunch of air tanks. Generally, if that's the case you're in, you probably should have avoided the air and used a motor system for that. But that just comes down to amount of power you need, amount of stroke you need, and amount of times you expect to fire it in a match.
One thing also about motors is that now, so in the past, we used to see that we had to be very selective about the motors that we use. Now we have motors like Falcons that can take almost whatever load we put on it, and they have the built-in encoders. And now the PDH has 20 slots, so you're not going to be limited on motors and have to use pneumatics as a supplement now. So it might be a good chance to try out during the off-season implementing some of these in terms of motors because it might be just more effective to cross out pneumatics completely, which is what we did this last year.
Yep.
So acquisition zone. It's so important to be able to pick up the game piece as effective as possible. So part of that is you want to minimize the amount of effort that your driver is going to be spending trying to get the ball or game piece. And so with that comes a large intake. You want to have an intake that you can operate very, very easily, and that now a lot of teams do over the bumper intakes versus going through the bumpers because you can just reach over. It makes the acquisition zone a lot easier. And we're going to talk about it in a little bit, but touch it, own it. If you have a smaller acquisition zone, it's going to be a lot harder to grab those balls from the side and sweep like we did this year.
Great. That takes us to golden rule number 4, which is rolly grabbers. Again, our golden rules are principles by which if you build to the golden rules and you incorporate all of them into your design process, we believe you will have a better season. Golden rule number 4 is rolly grabbers. I think if you're a team here that's grabbing cargo with your robot, there's a very good chance that you are incorporating the rolly grabber concept into your design. The concept is based around the idea that you can have a continuous intake, meaning you turn the intake on and you just keep it running, and then whenever you happen to interact with the game piece, you get the game piece, that whole touch it, own it concept that Austin explained. This is different than what might be considered like a single actuated intake, something like a claw where you drive up to the game object, and then once you have it in your claw, you actuate the claw, and it requires timing between the drive base and the actuator to get that. Versus a continuous intake, you might turn on the continuous intake and drive at the game piece, and whenever you happen to get it, you'll pick it up. The important thing about this, like in 2014, there was these big aerobics balls that were rolling around the field, and teams had to grab them. Some teams had continuous intakes, and they would just drive around with the intake on, and then when they came across the ball would get sucked up and into the robot. Some other teams saw this really large object, and they're like, hey, we need to build a big claw to go around and grab the ball. And so they'd have their claw open, and they'd drive at a ball, and they'd get to the ball, but if their operator wasn't right on the timing with the claw, instead of the claw grabbing around the ball, the base of the claw would hit the ball and bounce it ahead, and then they'd close the claw a millisecond later, and the ball would already be 5 feet in front of them, right? And so that whole timing that's required is something you're looking to avoid when you design your intake mechanisms. So having a rolly grabber allows your driver or your operator to turn it on and the driver to drive to the ball, and those two actions are decoupled so that you can acquire the ball quickly. And so it's easy in a ball game because almost every team here has a rolly grabber intake, but it's a concept you want to carry over to future games that may not be so obvious that a rolly grabber would be effective. Great. Okay, yeah. And this is the last part of the example. This is another pop quiz. We have 10 robots to look at here, so spend a couple seconds looking at these. Okay. And then a couple seconds looking at these pictures. And given all the pictures we saw and the topic we just discussed, what do you think all these robots have in common? Besides being blue and having similar drivetrains. Yeah?
Rolly grabbers?
All except one. Yes, the correct answer is rolly grabbers, except this one robot in the lower right corner has a actuated hook claw intake to grab the tubes that required timing from the operator. And this robot happens to be the only robot that 254 has built that lost at SVR. Every other robot they built that had rolly grabbers has one SVR. So if you like to follow trends like me, that's a pretty positive trend. And correlation may equal causation in this instance. So that's another practical lesson for rolly grabbers. All right.
Sweet. So we talked a little bit about pneumatics. But so the thing that comes with pneumatics is wiring up all the tubing and the VRM and your controllers for it. And so when it comes to electrical and pneumatics, you can do more damage than good most of the time when you try to overcomplicate stuff. So it's really important that we take the time to do it right, because you're going to be spending the entire season making small adjustments trying to fix it, and you're probably going to be making it worse in doing so. So we have a couple examples, 1678 on Einstein 2013, and especially, look at that rat's nest right there. How could you possibly diagnose what's going wrong with your can if you're looking at this? You couldn't even tell what wire goes to what motor. Or us in 2019, we weren't able to run any of our pre-written autos for Sandstorm because we had such bad can issues that we could not diagnose the entire season. And so keeping your wires, distinct from one another, simple. It goes straight from motor to motor. Try to keep things tied together so then you can diagnose issues of similar paths, especially with tubes for pneumatics. One really helpful tip is for your out and in, have two separate colors, or going to separate mechanisms, have separate colors for your pneumatics, just so that it's easier to diagnose. Because when it comes to all this stuff, it's almost impossible to figure out what's going on. It's kind of a magic can of worms that it somehow magically works and then somehow magically breaks.
Awesome. Okay. We said we'd talk about programming just a little bit. This is as far into programming as we're going to get, mostly because I'm not a programmer. But if you're to do just a few things going into the build season that are going to help improve your team's odds at competitive success, these are the 4 things that I would encourage you to have in your team's quote-unquote toolkit. The great part about this is a lot of these systems are a lot easier now than they were when I started giving this presentation almost a decade ago, because there's a lot of software and hardware actually that's come out over the last decade that has made all of these pieces of your toolkit more approachable, better documented, and easier to integrate into your team's workflow. But when I say toolkit, I mean, I think every team should strive to have at least one member of their team feeling confident in implementing each of these processes on a given robot, because there's a high likelihood that 2 or more of these will be required in any given game. So precision autonomous driving, this year is no exception. You get points just for moving, and you get more points if you can move to the right spot and do something with another game element. This is common in first games, so knowing how to program autonomous modes that drive to specific spots reliably and repeatably is important. Vision alignment is often a component of the game. There's new visual fiducials that are being introduced in 2023, which is an interesting new thing. There's a blog on it from First. If you don't know what I'm talking about, read up on that. But being able to align to targets automatically can speed up cycle times and can be a key part of your team's competitive success. Having the ability to control, oh wow, this is really old. I need to update these. Falcons or Neos. Well, who uses Talon and Magnet coders anymore? PIDs for elevator and arm, basically control systems in order to accurately move a mechanism from point A to point B with motors can be important given certain games. That was important this year, even with like the claws that went up and telescoping arms and stuff like that. All that stuff is important. And then lastly, having a controller for a spinning shooter wheel and being able to control the wheel to a certain RPM, spin up to that RPM quickly, hold a steady RPM so that your shots are more consistent and you miss less shots. That's an important element to be able to know how to do. And so having students with experience in all of these things before the season starts means that they can just, whip these out of their back pocket and use them in a given game that requires a similar type of mechanism.
So just to kind of do an overview of build season, so having an accelerated schedule is really important because you always have less time than you think you do. I know that we don't have bag anymore and that the entire season is more or less build season, but you still have less time than you actually think you do. When setting the schedule, we say aim for the moon, land among the stars. So you have a realistic goal that you aim for, and through effort and through effort and working through working to that schedule, you're going to have the time to do those extra things and get that extra practice that you need to succeed. Like I said, people always assume that there's more time than there is. We used to only have 6 weeks. Now we have, build season 2, but it takes a long time to do all of these, and we need to make sure that we get enough time. That each group, the programmers get enough time to properly program the robot. The electrical team has enough time to reliably wire the robot. Design has enough time to do iterative design and fail enough times so that they can, fix the robot. But if you have your schedule that goes up to, your week 1 competition, your robot's not going to be finished.
All right. Let's talk about build season, starting with week 1. Days 1 through 3 are brainstorming. We're going to stop and go to the next slide, which I'll dive into, which is days 1 through 3, brainstorming. On 1678, this is probably the most critical component of the whole season. This sets our trajectory for the year, and it's an incredibly collaborative and accelerated process that takes us from learning what the new game is to having a set of tasks ready to go for the rest of our season and a common goal for the team to aim for. The steps that we take on the brainstorming weekend, days 1 through 3, to get from the new game to where we want to be. Step number 1, we read the rules. This is incredibly important. If you had no idea how to play the game of soccer, you would assume that you could walk up pick up the ball with your hands and run it into the goal. This is obviously not the case. You must use things other than your hands to score goals, okay? And in FRC, you need to understand the rules of the game so you can know how to play the game. If you don't know the rules of the game, it will be ineffective for you to attempt to suggest mechanism or strategies, because there's a good chance that one of the rules of the game that you have not read plays a factor in whether or not your ideas will be viable. So we always start as a whole team with reading the rules, and we couple this with a rules quiz that every one of our students must pass before they move on to the next phase of the process with the team. So all the students read the rules. Our veteran students blitz read the rules and come up with a quiz that covers the rules. And then we publish that quiz to the team. And each of the team members take the quiz. And once they pass the quiz, they can keep reading the rules, starting to come up with ideas for the next step in the process. We also publish our rules test online. So right when we have it written, we will publish it to Chief Delphi. If you're interested in implementing this process into your own team, either the day of kickoff or sometime after kickoff, you feel free to make a copy of that Google Form rules quiz. It'll have all the questions and the automatic grading and all the little scripts and stuff that we put into our quizzes. Once we've all read the rules and have a basic understanding of the rules, we start to answer the what questions. The what questions are specifically around what will our robot do, not step 3, which is how will our robot do the task. Step 2 is incredibly important to decouple what we're trying to do from the specific mechanisms and solutions that might accomplish those goals. Okay? The what questions are going to be based around what do we feel is strategically viable, what are the tasks that we feel are within scope of what we're trying to accomplish. The how questions are built around how will the robot carry out the function, what are the designs that might work for that particular task. But we have to do step 2 before we get to step 3. I worry I'm explaining step 2. Austin, can you get more in-depth on what step 2 looks like?
Yeah, so the what are the ways that we can score, what is each task worth, what is the difficulty of each task. So for example, this year with climbing, is it viable to for us to build something like that in the season? Is it viable in the match as a strategy? So this is where a lot of we have students from our strategy team and mentors do a lot of point analysis to see if there's trade-offs and whether things are worth the value of designing towards that, and if it's a goal that we are required to have. A really important thing this year that we came with off of this was that our robot had to be able to sort balls based on the color that we were in the match. And so if we intook the wrong color ball, our robot would have to be able to filter. And if we didn't realize the point differential that we were possibly giving up, we wouldn't have been able to realize that. And so Karthik, in his presentation, goes a lot more in detail in this, but each team has a set amount of design points. And, you can do two easy things and one hard thing, or you can do 2 hard things. And so depending on the team, those hard things might be different things. A hard thing might be driving. A hard thing might be shooting, climbing. And so you have to decide with those design points what is a viable strategy for your robot in that year's game, because you don't want to allow too much for your robot to do. We set rules. The whats are, what does our robot have to be able to do? So everything that we cross off of our list for what our robot is going to do, we always clap and we cheer, because it's another thing that we're not forcing our robot to do every year.
Mm-hmm. All right, and after your team has whittled it down to a succinct list of the things that the robot must do, then you start to get into the how conversation. And the how conversation talks about how will the robot carry out the set of task lists that we've assigned to it in the what section. important things to consider when you're brainstorming designs for the house section is, do we have experience with a design like this? You can answer this question better if you've done a lot of the work in the preseason and build some of those projects we talked about in some of the earlier slides. You add those to your repertoire, and you can go back and lean on those in point A here. And then, how is the robot going to process the game piece? Not just how's it going to shoot it, but how's it going to handle the game piece while we have it? Those are all components of the sketching in the how process. On 1678, we discussed the how process via hand drawings. All of these steps in the process on 1678, we have a 100-person team. So the process looks like breaking out into small groups, and then each of those small groups in a setting like this, presenting to the rest of the team, and then we go back into small groups, and then each group presents again, and then we have some open forum discussion, and then we go back into small groups. The process goes over and over again. So to communicate ideas in the how section, we use hand drawings. The really important thing about the hand drawings that we found is you have to make sure that you're very specific about the scale of the drawings. A good example of this is in 2014. The game included these big track balls that you're launching over a big goal. The balls themselves were like 30 inches in diameter, practically the size of some robots that year, right? And it was really funny because we hadn't really fleshed out some of our processes for this, but we were still sharing hand drawings as a part of the design discussion. And a lot of students drew these robots where the robot was yay big and the balls were itty bitty little circles in their sketch, and be like, I think we'll have an intake that sucks up these tennis ball size looking balls into the robot, and then we'll have a little shooter that shoots it out. But the students weren't keeping in mind that the balls were actually massive, and there's no way that like two track balls were going to fit inside the robot in the way that they had sketched it out. So to communicate effectively, you want to pick the right scale and have students drawing their ideas to the same scale, understanding the rules around robot size, game piece size, things of that nature. And it helps unify the drawing language that each of you are conversing in with each other to share your ideas about the how section. And out of the how section on 1678, the output of that process usually looks like a couple of mechanisms that we know we're going to integrate into the robot because they're proven designs, and then a bunch of mechanism ideas that we know we need to take to prototyping groups. So part of the actionable output of the how section is a list of mechanism ideas that have been proposed as a part of this process that we need to learn more about via the prototyping phase, which we'll get into in a second.
Yeah, so our week one, it looks a little different now, but days 1 through 3, we spend that entire time brainstorming and figuring out what we're going to do, how we're going to do it, and what those prototype designs are going to be. On day 3, we start designing and manufacturing our drive base. We solidify what type of drive base we're going to be working with that year, and we start working towards getting driving as fast as possible. And through day 4 to the end of week 2, we're fleshing out prototype mechanisms. We're going to solidify how our drive base is wired, and we're going to get up and running with driving. We're going to make sure that we're going to start writing code for our autonomous, and we're going to start creating the program and iterating all of our prototypes and progressively make them more fleshed out.
Okay, and then at the end of week 2, we aim to have a finished drivetrain and have it wired up the following weekend and testing it for functionality. The important part of that process, getting that drivetrain built into the programmer's hands quickly, is so that, 1, your programmers have something they can start working with, and 2, you've already fabricated that component of the robot, and there's less remaining things that your hardware design team, your build team, whatever you want to call it, need to build later down the road. You front load some stuff to help remove some gating barriers for downstream customers, aka electrical, software, things of that nature, and let them start working as well. Versus a trap that a lot of teams get into is we can't start cutting parts until we've designed the robot. right? And the whole team is left there sitting on their hands, twiddling their thumbs. When is the robot going to be designed? When's it going to be designed? When's design going to give us a robot to build? And that is absolutely what you want to avoid. So we stage it on 1678. We get over the hump of designing a drivetrain, we send it out. We start building mechanisms in the following couple of weeks. But we'll start with the easiest mechanism that has the least amount of risk and scope, and we'll CAD it up and we'll build it right away before we finalize the design of, say, a fancy new intake or a new endgame mechanism. We'll just trust that we've allocated the space and the weight budget accordingly, but we got to get these systems out and get them to fabrication to build them. If we wait on the front end, everyone on the back end is going to suffer, and the schedule is going to crunch, and everyone's going to feel that pain. So we try to outfeed designs and outfeed mechanisms quickly and move on to the next step, with the goal being that we can integrate in around week 3, and by the end of week by the end of week 4, we have an integrated robot where the things that were the most complicated or took the most prototyping, sure, those are going to take the longest in design, but we haven't let other parts of the robot get held up by that, and we expect everything to still come together by the end of week 4.
Yeah, so golden rule number 5 is fail faster. So by day 29, we should have our fully finished robot. But that doesn't mean that your robot's ready to compete. And so, like I said earlier, you don't know what you don't know, right? You don't know how these mechanisms are going to properly play the game. You don't know how these mechanisms are where they're going to fail, where they're going to break. And so that's where we go through driver practice. I want to say Yi probably has a couple hundred hours of driver practice over this last year. And through that, we fleshed out different indexing problems with sensors, the way that we set up our can, the intake we redesigned a few times, our what we called the pooper this last year, to outtake the wrong colored ball. All of these different mechanisms. We don't see how they work until you have that fully finished robot. And so it might, in your head, work great, but then once you put it together, it could be, a dumpster fire and, could barely function on the field. Or it might be a great design, but it's too flimsy and it's going to break it once you hit the wall. And so once something breaks or something's not effective, that you need to iterate that design, fix the problem, and finishing your robot earlier and failing faster, knowing what's wrong with your robot quicker allows you to have more time to fix that and come to competition with a fully fledged out robot.
Yeah. Just to elaborate on that fail faster point for 1 second, I think a lot of times, at least I remember when I was a student, I remember growing up thinking that 254 must be perfect because they're so great on the field. They must never make mistakes as a team, right? They totally must be absolutely great engineers and designers and really smart kids that know how to build a great robot, right? And I think what I've come to learn is by the time we get to competition, 254 has failed way more times than we have. We had this insight this past year. We were practicing at their facility, and we happened to be around when they practiced their climb for the first time. And when I tell, I apologize because 254 might not like me saying this, but when I tell you it failed, all right? There were multiple parts that need to get bent with hammers and claws and things like that, but that's part of the engineering process. And what makes them such a great team is they work so quickly, and they've failed in so many ways that by the time they get to a match, of their first official match, they've failed way more times than we have. And what those failures do, they learn from those failures, they improve, and they don't experience those same failures when they get to the field. And we find in the rough seasons we're having, it's because we haven't failed in all the ways we should have at our shop. And we end up experiencing those failures during a real match. And that's not where we want to be. So failing faster, failing more often is a critical part of being an effective engineer. Great. So I feel bad because we kind of fibbed a little bit for the last 4 slides because there is kind of a new citrus twist to our build season. that we incorporated this year. I was talking with some people from Butte over there earlier today, trying to process through how to present this. But we're actually changing up our build style this year. And this is not going to be for everybody, but I felt like in full transparency, I wanted to share with you what we're planning on doing next season based off of what we learned this last season, and we call it our alpha build, okay? This on the left is a picture of our 2022 functional prototype that we lovingly dubbed Alpha. This picture was taken about 9 days after kickoff, okay? That's our team captain from last year, Ellie, standing next to the robot. The Alpha project was something that kind of grew organically this year. I was a little bit surprised by it. It wasn't something that we necessarily planned on. But the great part about Alpha is that robot that you see there is illegal in like 50 different ways, all right? It is not a legal robot for a whole host of reasons, okay? It's a drivetrain that we had lying around that was built previously. You can't use drivetrains that you built in past seasons. It had parts of the robot that were sticking out in various ways over the frame perimeter that were not possible to bring back into the frame perimeter. I don't even think by midway through the season, I don't think the intake deployed anymore. I think that system broke. And so the intake just always stood out. But what the Alpha build taught us was, one, we were able to validate. Remember Austin mentioned programming those drivetrains to run autonomous modes, right? And doing that early before the rest of the robot's even built. We were able to do that even earlier because we had this Alpha chassis built up, and we were able to test autos out, not just test auto paths, but once we got these really basic rudimentary rolly grabbers and ball funneling and shooter systems in place, we actually were able to run a 5-ball auto on the 10th day of build season. Right? Something that was a target for us, we're able to do early on because we used all of this old stuff and quick, rough wood prototypes that we had lying around and that we were building and testing to get the job done and allow that practice on the auto side. It allowed for early software development and especially driver practice, like Austin was talking about. Our drivers were probably more trained this year than they ever have been before, and a part of it is driver practice actually started day 10. It didn't start day 28 like we have done in the past when we built robots by the end of week 4. Driver practice started day 10, and it's because of the Alpha build. We started to understand the nuances of the game. What's the flow of the game? When you score into a hub, what's it look like to turn around and grab 2 balls? This might sound like minor, but it's something every team experiences at one point or another in their season. The issue is a lot of teams experience this for the first time either a week before their first tournament when they finally build their robot, or they experience this at the competition for the first time. Understanding the nuances of the game are really important for driving where you need to improve your design. And so building our robot early, we learned things like, hey, it's actually super important that we're not just sorting balls, but that we're quick at sorting balls. Because in our driver practice with Alpha, we wanted to drive into a pile of 4 cargo of various colors and come out with 2 of our own. And we found that without effective sorting, we'd pick up a bunch of balls and we'd have the wrong, even as careful as the driver was and wasting a lot of time, they would still pick up the wrong color ball. And it taught us how important the color sorting was. So those nuances start to get fleshed out when you have something like this. Now, this is not going to be for everybody. This is a whole lot of resources went into achieving this and kind of ungating a bunch of other teams' ability to develop, a bunch of other sub-teams' ability to develop. But in full transparency, it's something that we aim to do again in 2023, and we haven't fully formalized what this process is going to do to the rest of what you just heard about, which was our V1 schedule. We're going to go into V2, and we're going to have to make some updates to the slides you just talked about. We just don't know exactly what they're going to look like yet. So tune in next year when we give an updated presentation. But for now, just know that this is something we're going to be doing, and we're actually going to be even better prepared for the Alpha build this year. We're going to have more tools on hand, ready to implement right when kickoff goes, and build a very illegal, rough prototype by day 10 that can somewhat play the game, that we have no intention of competing with, but we want to build it for the sake of learning to inform our real robot.
I think that's the real takeaway with it, is that we have no intention of playing with this. If you look at this robot right here, it looks nothing like our robot this year. Every aspect of it is completely different, and it's a way for you to understand how a robot plays this game so you can better design your robot moving forward.
Awesome. We're running out of time, so you mind if I just blitz through the competition season information really fast? So a couple of highlights. I used to talk about how to take advantage of the bag. If you're newer to first, you don't know what the bag is, that's totally fine. You don't need to know. Basically, the competition season just looks like an extended build season. Take advantage of it. Watch other events and learn from them, and learn what you can glean from other events to improve your own robot. We like to do a little pancake party on the first week of regionals and districts just to watch what other teams are doing. You can see a bunch of our hardworking mentors cooking up pancakes while the students watch matches. It's a lot of fun, and it's a good opportunity to learn more about the game. So I think, in summary, Austin did a great job explaining Golden Rules 1 and 2 related to working within your means, preseason prep, drivetrain, golden rule number 3, please, please, please build the drivetrain you aim to build in season before the season starts and learn how to use it. Otherwise, skip it. Rolly grabbers in mechanism design. On the build season, Austin explained it really well. Fail faster. Fail faster. Learn what you don't know as quickly as you can. It doesn't have to be perfect. You just need your next round of learning, and you can go on from there. And then, I think that kind of covers what we want to talk about. Always check out these resources and our website, citruscircuits.org. This presentation will eventually make its way up there. We've given this presentation in the past, and those recordings are already on our website, as well as the PDFs of the slides. So we will upload those as well, so you'll have perfect quality slide decks as well to reference for your own team. And feel free to share those resources with your teammates that weren't able to make it today. Okay, great. Here's some of our contact info. That'll be in the slide deck as well, and we'd be happy to answer. Maybe we can get to like 1 or 2 questions as a group before we need to break, because we got to shut down and get out of this space.